Okay, here we are. This is lesson number 3, and we're going to expand our discussion to include confidence intervals. And the reason that we're going to do this is because confidence intervals are sometimes, very often, one of the most quoted statistics. And if you've ever watched the news around an election time where they give you the result of polls or telephone polls that they've done, they always quote a confidence interval. Newspapers, magazines, other forms of media very, very often will give this statistic. And it's very helpful to understand whether what you're listening to has merit or whether what you're listening to has no merit at all. So suppose that we want to report on the mean of our population. Right? We collect a sample so we can estimate the mean. And if we construct a survey or conduct a survey that's not a census, we can't truly determine any population mean, but we can determine a confidence interval that highlights the ranges where the population mean is likely to fall. So again, we're building on this notion of a sample approximating a mean. Confidence intervals kind of tell us the probability that it's going to approximate that mean.
Yep. How close
Are we to the mean value? Because the normal distribution is symmetrical, these intervals are of course always centered around the sample mean, right? So the closer our sample size gets to the number of members in our population and the smaller the standard deviation, the more confident we can be. So here's an example to basically start us off. And basically, this is a statement that says we can conclude that 95% with 95% confidence that millionaires donate between 12.6 and 17.4 of their income to charity. And so if we look at nothing other than what this sentence is telling us, it's saying that we have a 95% probability, right? So there's a 95% probability that if we take any millionaire from the population, that they will donate between 12.6% and 17.4% of their income to charity.
And actually, to just be a little more specific on that, this is a confidence interval for our mean.
Yes.
So in fact, it's saying that if you were to take a sample of 20, and then a different sample of 80, and a different sample of 100, and a sample of 500, and then a sample of 1,000,000, and take all those means, that we can conclude with 95% probability that any group of millionaires that you choose, if you average how much they donate, it should fall between 12.6 and 17.4%. So it's irrelevant, the sample size and the but that if you were to take averages of all kinds of different samples of millionaires, we can conclude with 95% probability with confidence that your mean will be like between those two values. Yeah.
So here is another example for us to go through. Let's interpret the statement. A study showed that 60% of first-year post-secondary enrollees do not come directly from high school. These results are accurate plus or minus 5%, 19 times out of 20. So how do we interpret what this says? Because there's a lot going on here. We've got a plus or minus 5%, we got 19 times out of 20, we got a 60%. Where does all this come from? And what we can do first of all is we can say, okay, 19 times out of 20 is telling us something. That's telling us that this probability, the probability of this happening, these results happening, are accurate 19 times out of 20. If we turn that into a percentage, that's 95%. So this is a 95% confidence interval that we're actually talking about here. And in this particular study, a study showed that 60% of first-year post-secondary enrollees don't come directly from high school. These results are accurate plus or minus 5%. So what does that plus or minus 5% have to do with this 60%? Well, it basically says that there's a 95% probability that anywhere from 55 to 65% of post-secondary enrollees do not come directly from high school.
And again, that's the mean. So whenever they're reporting on the mean or reporting on the average, this is a confidence interval that is centered around your mean. So you could expect that no matter which samples you picked, how many were in your sample, where you got them from, you could be 95% sure that the mean that you calculate based on your sample should be between 55 and 65%.
Yeah.
Yeah.
And yeah, because here the mean would be of course 60, and so this is our interval.
Yeah. So they're
It's from
reporting
that.
60, but then they're giving you a window that within that window we can be 95% sure.
Exactly.
If you go grab a bunch of post-secondary enrollees and poll them.
Exactly.
Yeah.
Okay, so Ms. Hughes, let's go through basically how do we create them? We can interpret them, but interpreting them is different than creating them. So how do we create a confidence interval so that we can say, hey, here's some research that I did, and I'd like to be able to tell other people this is how confident I am.
So, because it's a confidence interval for your mean, let's say your data that you've collected in your experiment or in your survey is normally distributed, you found your mean or your X-bar for your sample, and you want to be able to report that mean to the public and say, oh, it looks like 68% of, doctors do this. But you recognize that you've just had a sample, you don't have all the doctors in the world, so you need to give them that confidence interval. Here's how you do it. What I'd like you to look at first, because a little bit less confusing, look at the one that's on the right. Okay, this is just a formula that we're going to use to generate a confidence interval for your data, okay, around your mean. So of course we start with the mean because we're adding and subtracting a window. In the previous example it was a 5%, up and down off the 60, but we're going to add and subtract a little window that we're going to create as our little interval, and then we're going to assign a confidence level to it. So here's what we do. This Z sub alpha over 2, okay, is just the Z score for your acceptable margin of error. So notice how here, if it's a 90% confidence interval, then it's a 10% margin of error, which means that on either side of your normal curve would be a little 5% tail on each end. And if you were to go and look at your Z-score table and look at where a 5% probability lies, it lies at negative 1.645. And then when you look at where a 95% probability lies, it lies at positive 1.645. So this Z-score, if you multiply it by your standard deviation over the root of your sample size, so this is sort of an arbitrary value, but we take our standard deviation. If it's small, okay, so if we've got a sample that's tightly clustered around the mean, then we're going to have a tighter confidence interval. If it's very spread out, so this is why we use a standard deviation, then we're going to have sort of a wider interval, a range of values around our mean. So we divide by root n. Again, the larger your sample size gets, the larger this denominator gets, which makes this value get closer and closer to 0, right? So if we ever did get the whole population, then we could expect to add or subtract a 0 to the mean, which is, of course, just what we would think, right? So this Z alpha over 2, which is your Z score for the acceptable margin of error, these three values, you're going to just put them right onto your reference sheet along with the confidence intervals.
Exactly.
You don't have to tabulate them or calculate them or pull them off the Z score table.
These are basically constants.
These are constants.
For the purposes of our students in our course, I would say that if you need to know the confidence level for whatever example we give you, 90%, 95%, 99%, you are going to be given, or you should write these on a reference sheet, on a study sheet, so that you could reference them during a test. You don't have to look these up. You don't have to find them. That's a little bit beyond the scope of our course.
That's right. We won't ask for like an 85% confidence. We won't ask for something weird. We'll ask for one of these three. These are the typical ones. Okay. So basically what you do is you take your mean and you add this constant times your standard deviation over root n. That would be the upper end, and then you take your mean and you subtract this constant times your standard deviation over root n, and that would be your lower end. So this is that plus or minus 5% or whatever they were talking about. The way that looks in interval notation, so if you've taken advanced functions already, then you know the left end of your interval and the right end of your interval are in the brackets with a comma between them. So we have the mean minus the z-score times sigma over root n, all the way up to the mean plus the z-score times standard deviation over root n. So that's your left and right end. This means exactly the same thing. If you want to write it in interval notation, then once you've done your calculations, you'd separate them out that way.
Interval notation is like for showmanship, really.
Yeah, it's just fancy.
Yeah, it is. It's fancy.
Absolutely. So we, of course, we do it fancy style here, but you've got options. You've got options in your homework. Data management's
fancy too.
We don't even mess around here, people.
No.
All right, so let's suppose we conduct a survey of 19 millionaires. That was as many as we could find. So n
Yeah.
equals 19.
I don't know 19
I don't know
millionaires.
19 millionaires either. Wish I did.
Yeah.
I would still be doing this, students.
So would I.
Okay.
So would I.
To find out what % of their income the average millionaire donates to charity. Okay, so now we've grabbed a different sample. Okay, so the ones that we were reporting on in the beginning, that's not our sample. We've got our own 19. We're going to have a look at them. We discovered that the mean % is 15. So they donate, on average, our 19 millionaires, when we find the mean, is 15. And the standard deviation that we found, the S that we found, is 5%. So assuming the distribution of all charity percents is approximately normal, this is the key thing.
Yeah, because the thing is, we can basically go on and on. If we don't have a normal distribution, we have to use a completely different type of statistics. Yeah. And that's like second, third, fourth year statistics.
Yeah.
And we're not even going to worry about that.
We're in like negative first year statistics.
Yeah, we're in negative.
We're in T
negative,
minus one.
Yes, exactly. T minus one first year statistics.
So yeah, we're not gonna worry about those other distributions yet.
But basically, all of your questions in this section are going to say, assuming the distribution of whatever is approximately normal, find this.
So you just go ahead and assume.
Yes, go ahead.
Because we're going to tell you what to assume.
Yeah.
All right. So we want a 95% confidence interval for this mean and this standard deviation, okay, of 15 and 5, and the sample size of 19, okay? So that 95% confidence interval, we just go back to the table, so just back up like 3 lines, and we say, all right, so the acceptable margin of error, okay, for 95% confidence interval, the z-score that corresponds with that is 1.960. And we've got our mean is 15%, we've got our sigma, our standard deviation is 5%, we've got our n is 19, okay? So we're going to set it up so we've got the mean minus the z-score times the standard deviation over root n. So we've got our standard deviation here and our root 19 there, all the way over to our mean plus the z-score for our acceptable margin of error for our confidence interval times 5 over root 19. So everything is the same, except there's one's a minus and one's a plus. Okay? So then when you perform this calculation, and don't forget BEDMAS, okay? So do what's in the brackets here, and then perform your multiplication, and then perform your subtraction. If you've got a good calculator that will do this for you, and understand that you want scientific, BEDMAS, right? Then you may be able to jump right to the next line that I'm going to show. So right now it's 15 minus. I calculated that product at the end, so 15 minus 2.248 and 15 plus 2.248, so that the left end of our interval, the lowest value, 12.752, and the highest value, 17.248, we can say with 95% confidence that the mean amount that millionaires donate is between 12.8 and 17.2% of their income, right? Yep. So the desired confidence interval for our mean of 15 is actually 12.8 all the way up to 17.2%. So we could say with 95% confidence.
Yeah, and it's very interesting to note, we had a sample size of 19, which, we made a joke about earlier. That would be a lot of millionaires to know. But the reality is that look at what happens to your sample size if it gets much smaller. Look what happens to this confidence interval. Yeah. If the sample size gets small, like if that root 19 goes down and down and down and down and down, and so maybe we pull a sample size of 3 millionaires, right? Then all of a sudden we're in a situation where our width of our interval gets so much bigger because this factor right here gets bigger. And so now when your sample size goes down, your confidence interval really goes, it goes much larger. And so that's not desirable.
But that makes sense.
But it does make sense. A small confidence interval comes from having a small sample size. And then there's other factors that affect it as well. But we need to make sure that we note here, okay, the more confident we are, comes with an increase of sample size.
That's right. And so we get to tighten and tighten this interval closer and closer to that mean of 15 if we had a much larger sample size or if we even had a smaller standard deviation. If millionaires could just make up their minds and all donate around the same amount, then we'd have a tiny little standard deviation up there, and then we'd have this huge sample size, and it'd be like 15 plus or minus hardly anything. right? So that's how you can take a confidence interval and increase the specificity, is to really go up in your sample size if possible, right?
Or down in your standard
deviation. But again, that's the population. Sometimes things are spread out. What can you do?
Now, in recent years, basically statistics in the social sciences, such as education or other areas like psychology, sociology, have been reporting 95% confidence intervals.
That's sort of the standard you'll hear.
That's the standard you hear. And really, you'll kind of look for results that have that, well, in layman's terms, maybe 5% of this is due to chance. Yeah. But I am 95% confident that this is... In recent years, however, if you look at current research, a lot of times people aren't really accepting that 95% confidence interval anymore. They want more confidence, so they're going to a 99% confidence interval. And so it's becoming much more popular to quote probabilities and to quote confidence intervals that are a little bit tighter. Yeah. And because if you could say, hey, I have a 99% confidence interval, that, you know, basically this is our interval width, and you can keep that small, then there's a little bit more clout, so to speak. Yeah. So let's do a 99% confidence interval for the mean percent. Same example. 99%.
We all the same stuff, but this time we want to be more confident. And to be more confident, we're going to have to widen the interval a bit.
Yeah, right? Of course.
If I want to be more certain that my mean is going to be here, then I might have to widen out that interval. So if we go...
It's a trade-off.
It's a trade-off, right? You can be more confident, but then you have to create a wider interval.
Yeah.
So a 99% confidence interval, again, you're just going to take this right from your cheat sheet or your... the page that we have right here, those couple lines above you.
Yeah, because Z alpha over 2 is now a little bit bigger.
Yeah, so 2.576, so plus or minus 2.576 will give you that 0.5% tail on each end of your normal curve. And so if our mean is 15% and our standard deviation is 5%, our sample size is 19, nothing else has changed. It's just that now, in order to up the confidence, we're going to have to widen the interval width, and that's fine. So now we're going to do 15 minus 2.576 times 5 over root 19, all the way to 15 plus 2.576 times 5 over root 19. Again, I'm going to find those values when I take 5 divided by root 19 and hit equals, and then times it by 2.576. So that means we're adding and subtracting 2.955, right? Which is higher than the one that we were doing before.
Yeah, exactly. Yeah.
But that's okay, because we want to be 99% sure where the mean lies.
Okay, so let's expand the confidence interval.
That's right. So now we're going from 12 to basically 18%. So now we can be sure that the mean is between 12 and 18%. We can be 99% sure that any bunch of millionaires you ask are going to have an average donation. Okay, so it's the mean that we're talking about, not the individual values. And so then the desired confidence interval for our mean of 15% with our sample and our standard deviation runs from 12% to 18%. So we've just rounded to 1 decimal place here for your confidence intervals. Yeah.
So that concludes this lesson.
And concludes this unit.
And concludes this half of the course. You're now halfway done.
Yep.
Data management.
Good for you.
If you're studying along with us. Thank you very much. Ship shape and have a good night.